Professor Ima, who's visiting us from UC Berkeley. He's a professor, very quick introduction of Professor Ima. He's a professor at the Department of Electrical and Computer Science at the University of California at Berkeley. His research interests include computer vision, high-dimensional data analysis, and the intelligence system. Professor Yi received the bachelor's degree in automation and applied mathematics from Tsinghua University in 1995, and the PhD degree in electrical engineering and computer science from the same university where he's teaching now at UC Berkeley in 2000. He then joined the University of Illinois Urbana-Champaign ECE department from 2000 to 2011. And then he has been principal researcher and manager of the visual computing group of Microsoft's Research Asia from 2009 to 2014. And then the executive dean of the School of Information Science and Technology at Shanghai Tech University from 2014 to 2017. Professor Ma has published extensively in the fields, in conferences and journals. He has also co-authored 3 textbooks in computer vision, generalized principal component analysis, and high-dimensional data analysis. He received the NSF Career Award in 2004 and the ONR Young Investigator Award in 2005. He also received the David Marr Prize in computer vision from ICCV 99 and many other awards throughout the years. He has served as the program chair for ICCV 2013 and the general chair for ICCV 2015. He's a fellow of IEEE, ACM, and SIAM. Welcome, Professor Yi, and we look forward to your presentation.
Yeah, thank you a lot for the nice introduction. Also, very happy to, very glad you guys. Thank you a lot for having me visit. It's a fabulous place. Honestly, it's my first time in Abu Dhabi and also in this university. I was very impressed so far with everything you guys are doing here, the new city, and also the everything is uprising and constructive, and also very, very exciting time and place in the world. So so today I'm going to give a little talk about some of the recent work we did in the past few years. Right? So I'll see there's actually a lot of collaborators, students at Berkeley, and also and so on. There's also folks at Harry Sham, also the former director of MSI, actually got involved with this work. Just give a little bit of history why we did this, right? This is called closed-loop data transcription about reproduction. Actually, everything started about a few years ago, 3 years ago. Was visiting Yang Kun. He got a Turing Award. We were good friends. So I was in New York in his office. We spent about afternoon discussing, what deep learning was all about. And we spent the whole afternoon chatting one question. What is deep learning, deep networks trying to optimize? Trying to do, right? Actually, at that time, I was a little bit surprised, right? He's really the pioneer of this. Still, there's things we don't know about it. Actually, rather fundamental question: what deep networks trying to do, right? Definitely not fitting labels, right? Labels can be wrong. What is it really trying to do? Why it should be successful? So after that, of course, that was November 2019. Everybody knows shortly after that what happened, right? Pandemic hits, and so everybody gets stranded in my house. So we actually, my students, we're started working on this topic. Can we understand deep learning a little bit better? Right? That's sort of set up for it. And today I'm going to talk about that series of work. There's no deep learning in the title, and you'll see why. Right? So first thing, of course, for that this is the 10 years, right, of the revival, dramatic revival of deep learning. So maybe we can put some thought to it. What we have learned, what we have done, right? Can we actually understand this from a probably bigger picture? Sit back a little bit. Right? The first, that in the past 5 or 10 years, right? There's lots of after the deep networks, deep learning, and there's a lot of theory, algorithms developed around it, applications around it, and especially on the theoretic side, people try to understand deep learning. Actually, try to study deep networks themselves as object study. So we actually took a very different route. Right? If there's something to deep networks, so deep learning, I mean, they must serve some purpose. Right? So then we can step back a little bit. Ask, what do we want to do with learning? Right? What do we want to learn from data? Can we figure out that? So that may answer the question that Yang Ku asked, right? What deep learning trying to optimize? Try to learn. So what do we try to learn from data? So we'll set that straight. Then we'll see that maybe, just maybe, right, deep networks become the means to the end. It's not the subject. It's not the object of study. It serves some purpose to be able to understand things better. So that gets us to understand, so for example, in terms of learning, right, then what do we want to learn from the data? Obviously, we want to learn the data structure, the information carried through the data. If the data doesn't have structure, doesn't have distribution, doesn't have something for us to learn, there's no point of learning anything, right? So obviously, if you try to start ask questions that what do we want to learn from the data, what is the information, what is the structure encodes that data, obviously falls in the realm of information theory. That's precisely what it studies, right? How do we quantify, measure the information carried in the data, right? So we'll see that how do we use an information theory to characterize what do we try to learn from it. Right, set the object, we actually call this, from coding theoretical point of view, there is a very intrinsic measure, computable measures, we call it coding rate reduction, that set out very, very nice objective for us. Now, obviously that once you're very clear about what you want to do, the rest of things just optimize, solve the problem, right? You have a very clear target. How do you achieve that target? You can measure it. You want to achieve it. The best thing to do it, there is already existing field called a control. System theory, precisely try to achieve a given task. Right? You see that how do we achieve such a task very efficiently, effectively, through a closed feedback control. Right? There you actually will see where deep networks arise, try to achieve. And really, that this is things that we start to realize, and maybe, just maybe, right? Right. The revival of the network just was able to discover one piece of what we call a really complete intelligent systems, right? Where information theory, control, optimization, deep networks all play their own role. They are necessary pieces into something that we can integrate. Really strive for intelligence. We call it, they are actually the cause of the emergence of intelligence. We start even to drop the name artificial intelligence. Why? If anything is intelligent, right, they have to follow the same mathematical principles. We call it the two principles. One is parsimony, which precisely characterizes simplicity, the goal of learning. Then the self-consistency, try to achieve the goal in a self-consistent way. So let's just start with, so how do we get things started, right? So the point is we want to be a little bit, fundamental, a little bit, nature doesn't know anything, right? I mean, we have to start off with something very, very basic, very, very simple, primitive, right? Making the minimal assumptions, right? We just, for example, our world, maybe the outside world, right? We assume we see a lot of data, images, audios, doesn't really matter. We use the images as examples, but it applies to everything else. We're seeing a lot of samples, data, images, right? They may belong to multiple categories, many, many objects, right? Each category of objects must have some structure, right? The image of apples must be something common to them, right? It lies on some low-dimensional, for example, low-dimensional manifolds, right? Those are apples, oranges, and so on. And now what do we want to learn from them? Right? We see those images all the time. Internally operate, maybe just trying to learn, try to find a very compact structured representation of the data. Right? Still very conceptual. We want to make it very simple, very compact, very structured in our brain, which are encoded. Right? So it's useful, it's very easy to store, very easy to access. This seems to be a reasonable thing to do. Turns out this is exactly what the deep learning is trying to do. Right? Deep learning is actually, in the first practice, that's very lucky. Right? That actually chose out the, let's map those multiple categories. Let's say 1,000 categories on ImageNet. Let's map to this one hot vectors. I can actually assure you, if they use a different way to encode the label, class label, they won't be successful. Right? There's reasons to that. Right? They actually happen to choose, let's map each classes to this one hot, one directional vectors. Right? Of course, naturally, they wanted to maximize this or minimize the cross entropy. Right? Essentially says that I try to maximize correlation between the output of some networks and those one hot signals, one hot vectors. Right? Of course, I don't know the mapping, hence I can model with some deep networks. That's what really it is, right? And this is cross entropy. Everybody sort of practice this, knows how to do this, right? Just fits label and learn the network. And you can use it for classification and so on. Of course, what you get what you reward, right? Here, you want your network to output a one-dimensional vector that correlates with class label. You get what you want, right? This is what the latest work from Donahoe says. Precisely, if you train a network like this, all the features learned by the networks are going to collapse on this one-dimensional singleton per class, right? This actually gives you very good classifiers, even generalizable to some extent, surprisingly. Now, the question is, our brain doesn't function like that, right? It's not just an open loop. It doesn't just give an apple, says it's apple, right? In fact, we want to know what differentiate apple from oranges. We want to generate. If I close the eye, I can draw what apple looks like, right? So this is the thing that can we actually generalize this a little bit, minimum to start, right? So if I have data lines of multiple submanifolds, maybe I want to capture everything, all the characteristics, instead of mapping to a one-dimensional vector. One-dimensional features, those discriminative, but I also wanted to keep all the features that makes apple, right? Map to some subspaces. Maybe the intrinsic degree of the freedom of the distribution of apple is 5-dimensional. Then I may be better map to 5-dimensional features, right? Of course, to borrow what from one hot, I wanted the different classes to be maximally coherent. So this you can think about, even this is the first step to just generalize what we already practiced extensively with deep networks, map to one hot vectors, right? There's much more to it. Right, now, what we're doing here is actually already changing the problem a little bit, right? We no longer focus on the label. We focus on what makes label meaningful. We try to learn the structure of the data. So you have probably saw information bottleneck information, try to explain what the network to do, right? They always try to focus on the labels, right? While they try to get the maximum information on the feature, maximally correlated with the feature, the label, rather than pay attention to the data. Here we try to shift that attention back to the data. What do we want to learn from the data? What does the structure of the data make the label mean? So now, since this also put us in the driver's seat, okay? I'm no longer distracted by the labels. I want to understand what the data. Right? And since I'm in the driver's seat, I better stipulate all along. If I spend $1 million to train something, I better be clear what I want out of it. Right? So, what do we want from this multi-class of data? I want to learn some representation, right? Each class, I better make them linear. Right? The distribution, original distribution may be nonlinear. It's very complicated. But I want to make it simple. Right? Second, of course, I wanted to compress. The original data here could be an image, right? Which could be a million pixels. But that's too redundant. Maybe I can reduce to 200 dimension. Compress. Right? Second, I also wanted those subspace to be orthogonal, incoherent. Why? I can encode with different neurons. Each neuron is very sparse number. I only have to encode each basis separately. Right? The firing will be sparse. It's associated with all these compact representations. And finally, how in the world I know this is right? Map this to this. How do I know if this is a 6-dimension? What if this becomes a 5-dimension? I underfit. What if this becomes 7-dimension? I overfit, right? How do I know this mapping features are good enough? Obviously, you have to go back, map it back, right? So why do this? So this is the first sort of our wish list, right? Put ourselves in the driving seat. I want to learn this from data, okay? May or may not we be able to achieve this, but this sounds like a reasonable thing to do. So now the question, let's kind of be a little bit formal about this, right? Quantitative, right? So this is my wish list. I try to learn mapping from my data, X to Z, so that each class becomes compressible, mapped to a linear no-dimensional subspace. The dimension of the subspace corresponding to the distribution of the data. And also between class, I want them to be very incoherent. They better be orthogonal, independent, right? Geometrical orthogonal method, statistically or probabilistically independent. And of course, I want every class to be maximally informative. I want to know everything that apple, differentiate apple from oranges, not just a color, not a very, discriminative classifiers, right? Let alone some computers also call it apple. Okay, the label means nothing, right? It's a structure of the data that we're going after. Now the question is, how do you measure, right? So since we're going for compression, we want to linearize things. How do you measure the final result? You need a very good measurement for that, right? So it turns out this is precisely we go back to information theory, right? If I have data drawn from subspaces or Gaussian sources, information theory told us that the number of bits, actually the natural measure of the information in your data spanned by the features or spanned by your data is actually the volume. How much volume is spanned? Right. See, if the data is uniform, it's a generic Gaussian in the world or in the original data spaces, there's nothing to it. Okay, whatever you learn, whatever you compress, you lose, right? There's nothing to predict, there's nothing to generalize. So you're actually essentially capturing the low-dimensional structures. They can generalize. So then the question is that how do I measure those, right? The volume. Turns out that this is information theory says, well, a very easy way to measure the volume of any distribution is packed spheres, right? If I give you a bag, what's the volume of the bag? 4 beans in it, right? Then count how many beans in. Of course, more accurately volume, you use smaller beans, right? So basically, this is precisely tells you how many spheres you can pack in your distribution, support of your distribution, subject to any precision, epsilon 1, right? Turns out, if your data from a subspace of Gaussian, there is a closed form formula, very magical formula for Gaussian or subspace data. Turns out this formula actually is exactly the same. Doesn't matter if your data lies from a subspace, has no probabilistic interpretation. You can derive the same formula with the same coefficient from just quantify the SVD purely algebraically. You get exactly the same formula. Or you can derive this as a Gaussian source, and that's the redistortion. Very, very interesting. And we'll see actually entire neural network comes on this. So now, here the problem becomes very simple now, right? So I have data, of course, original data is not Gaussian. If not, I make them Gaussian. I make them subspace, right? The original data may be nonlinear. I make them linear. That's the whole point. That's exactly the role of a data network. We're trying to learn such a nonlinear mapping such that the output becomes something we wanted, right? Becomes subspace. Right. So if the feature becomes Gaussian, then I can measure. This becomes very, very intrinsic, very, very close form. Of course, the data is not necessarily a uniform Gaussian, right? It's not. So there are multiple classes there. Hence, each class may be mapped to a low-dimensional subspace. I have the partition. Of course, if I know the label, I know each one on different subspaces. Each manifold X mapped to its own subspace. Then, of course, I can measure the volume of each of the classes. Each one is a subspace, right? I use exactly the same formula. Only have to sort out which point belongs to which class. That's it. This is exactly the same formula, by the way. It looks a little bit complicated, but it's exactly the same darn formula. Just apply to the data belongs to that group. Take average. Hence, this is the volume for all the features expanded. This is the volume for all the subparts, each subset expanded. Right? Then naturally, remember that wish list. We want every class to be compressed, linearized. We want different classes to be orthogonal. Naturally, what do? You take the difference. You want the whole is maximally greater than the parts. Right? So you take the difference, make sure the whole, this is the volume for the whole, this is for the parts. Right? Therefore, you try to maximize this. The larger, the better. Essentially, already this formulation contains all this contrastive learning, contractive learning, right? Since they're similar, belongs to the same class, should contract. Since it belongs to different classes, should be contract, right? Hence, contrastive learning, contractive learning, right? All those heuristics people are playing with pairwise. Here is a set. the whole sets. We measure the distributions. Intuitively, forget about this, right? This thing, this looks a little bit complicated, but try to pay attention. Right? This is log determinant of some covariance matrix on each part and so on. Whole depletor will come from this. But for now, this is very intuitive. This is like a simple to the bone, right? All it measures is that, remember, the first term is measuring the whole volume. How many spheres you pack into that, the whole space, finite features. And the second term are just all the screen beams, right? Where the data actually lies on subspaces. Hence the difference maximizes space in the blue. How many spheres you can pack in between. That's a natural distance between degenerate distributions. Remember that, right? So hence why we prefer the one on the left. Everyone prefers the one on the left. Why? It is incoherent. The features are orthogonal, independent, whatever you call it, disentangled, whatever you call it. Okay, all the language people like to. Machine learning likes to make the jokes, right? Mathematics, Tom Carey said, right? Mathematics is the art of giving the same name to different things. Machine learning is the opposite. So, well, now let's just look at this a little bit, right? So if this is what we want, right? All we do is try to learn a mapping from X to Z. But it's stopped working. Sorry. Oh, this started working now. Okay, so mapping from X to Z so that Z, in terms of this measure, delta R gets maximized. Right? We call it the maximum coding rate reduction. The whole reduced to parts. You maximize that. Right. Now, suddenly you say, oh, wow, this is interesting, right? So we only have to maximize the how many, whichever the representation should maximize the blue balls, space of the blue balls. Great. If that's what we want, let's just scale what's on the left twice, 3 times. You can pack more blue balls, right? Now, of course, everybody in this room will profile, right? This is not fair. Why is it not fair? Scale is not normalized. Everybody needs to normalize. If you want to compare 2 representations, you normalize the scale. Very, very simple to that. Hence, what do? Every layer, you normalize your scale, the features. That's it. Of course, in practice, right? People do batch normalization, layer normalization, instance normalization, spectral normalization, group normalization. God knows how many normalizations they can come up with, right? They're doing exactly the same thing. You normalize the scale so you can compare different representations at different layers or different networks. That's it. Maybe different normalization good for slightly different data, but mathematically they're doing exactly the same darn thing. Okay? So the other question is, does this really give you the job? Does the job you want? Remember that wish list, right? Yes, it does. This is our next paper, 2020. Turns out if you just maximize this quantity, you get the feature precisely mapped to orthogonal subspaces. And not only that, each subspace actually becomes maximally informative. Actually, they're distributed almost nearly isotropic. They're orthogonal, they're isotropic. Right? So we changed Aristotle's slogan, right? The whole is greater than sum of the parts. No, we want the whole is greatest, maximally greater than sum of the parts. That's what we want for representation learning. So the question is now, this is on the real data sets. Let's just try and have some fun, right? You can actually can train neural networks to learn this mapping. Now, instead of have to check, after training to check on the test data, how good my feature is by classifying. No, you don't have to. Now you can actually monitor in 3 physically, statistically, geometrically meaningful quantities, right? The volume of the whole and the parts and the difference, right? You can actually monitor the process, so how your learning is doing. Once it stabilizes, it stabilizes. And because you see, this is on the CFA 10, right? Suddenly you get exactly what you want, right? So that the 10 classes, they're not collapsing. So this is using this is compared with cross entropy and the user. The only thing you do is change the object function, right? The same network, the same data, the same optimization. Nothing, everything is exactly the same. The only thing you change is the object function from cross entropy to the maximum coordinates, MCR. You can see that the 10 classes gets learned are orthogonal. Absolutely, there's no crosstalks. Right? And each one becomes a subspace, right? Not collapsing. Like here, you get it come close to 1-dimensional feature. And suddenly, since every class becomes a subspace, what you can do, you can fit a PCA, you can fit a subspace to it. You can compute the principal components. You can find all the images that align with each of the principal components. This is not from the label, right? This is actually automatically each class becomes 10-dimensional. And you can see that each coordinate is very, very meaningful. Birds, right? Every principal component. You can sort it out automatically. This is original data. Later on, we're going to see how we're going to regenerate data from this. And one thing good to come out of this is that because we shifted attention to the data structure, right? And remember the deep networks, right? If you fit the label, if the label is wrong, for example, 10%, 20%, all the way to 50%, labels are wrong. What do? The network is going to fit every bad labels, right? Then you suffer. But turns out, if you try to learn the subspace, the manifold, the majority samples matters. That's much more stable, much more robust, degrade much more gracefully, because you're not committed to every single labels. That could be wrong. You only compress what can be jointly compressed. So now the question is very interesting, right? I don't have time to talk about this, but I'll give you the so far we learned this mapping. We still use mapping using ResNet, right? Uses whatever your choice of network to learn this mapping f of x. Why? There's no guarantee in residual network or any network can model this mapping. Maybe we're just lucky, right, for the C form. Although a lot of data, you may not be successful. The good thing about knowing exactly what you want to do, knowing clear the objective, is that you couldn't care your deep learning or shallow learning, right? You're just trying to learn that linear mapping. If you're lucky, you can guess the kernel, for God's sake, right? It may be polynomial works. Who knows? Not the rest of it, right? So now the question is, since my job is just maximize delta R, why can't I just directly optimize this entire thing? Right? If I'm a god, if I maximize this, I'm done, right? I learned the feature I wanted. Right? So of course, but unfortunately, this darn thing is, you remember that log determined, right? There's very non-linear, non-convex, but they're very structured. Right? It's non-linear, non-convex, nothing else we can do. The best we can do is probably the greedy descent. Let's just do greedy descent. Of course, everything has to be normalized, restrict out the sphere, so hence it's projected greedy descent. Let's just do that, right? Now, since everybody believes greedy descent is magical, so all we're doing is that, see, this is my original data, right? On those manifolds. I want to map them to this orthogonal subspace, right? Those dotted line. So I don't know how to do this globally, but at least I can do locally, right? I push things apart. I push those things locally. So follow the gradient flow, moving things incrementally. What do you get? Once you compute the gradient, something magical happens, right? The gradient, the flow is very, very structured, right? The gradient flow looks just like this. This is the G, stands for gradient, right? There's a part, remember, there's a whole part that's expanding. Each class you're seeing is compression, right? You're trying to linearize, compress them. That actually just falls up out of the derivative. They're exactly linear operators acting on the features. Some are compressing, some are expanding, right? And you really recognize what this looks like if you draw the diagram, what it does to the features. Just look like a residual network. In fact, even better. In fact, this just res next precisely try to emulate this. Multi-columns works better, right? And here you derive everything from scratch. Here, there's a very, very big difference, right? There you actually guess, you try for years of trial and error, right? You randomly initialize. Here, you construct one by one forward. There's no guessing. No guessing of this architecture. No guessing of every single operator, every single parameter is derived from scratch, from the data. There's no random initialization. Everything's forward. So there's actually 1 hour talk I gave last year about this. It's called a white box. Also, there's a paper, a white box deep network from rate reduction. You can show that. It's about 100 pages, but can't read it. So this sort of turned 70 years of practice with neural networks very much upside down, right? So this left column sort of summarizes what we've been doing since 40s, 50s, right? We always try to use the network to fix the input-output. We guess, for many years of trial and error, we guess what the architecture looks like. And each operator is kind of empirical. We don't know what it really does. It's all guesses. And for invariance, we try to, let's do something n plus 1 augmentation. And the network are randomly initialized, right? Then we backpropagate training them. After training them, we get a black box, right? Even the representation, the features, well, something we call them hidden or latent. Right? Even this is a little bit ironic, right? I spend billions of dollars train a network, yet I call it a hidden representation. I don't know what I've learned. Yes, the input-output helps me to do something, but really nothing I can diagnose, right? Understand, interpret. So now actually this is very, very different. Our job is just compress, right? So then the object function is reduction. Nobody gets to decide anything, not even the coefficient, right? And the architecture just iterative optimization. Everything gets, we know exactly what each layer is doing, right? And that's, actually turns out if you enforce your compression to all the shift environment versions, then the gradient operator ENC automatically become convolution. You derive convolution neural network from scratch. You don't get to choose it. Not only that, those convolution neural network has its own structure. You can read the paper, right? It's more efficient to do it in the frequency domain, not in the time domain, right? Hence, our brain is computing frequency. And also, the network is forward constructed. And it turns out, since it's forward constructed, you can do optimization either forward or backward. There's no differences. It's just tweak, fine-tuning the network, fine-tuning the optimization algorithms. In the end, you learn a white box. The feature you learn is also white box. Object function is white box, network is white box, the representation you learn is white box. There's absolutely nothing black. Right? So this is actually one practice we sort of set out to do, right? So from X, just recap this, from X to Z, we try to learn the mapping such that maximizes information-theoretical objective function, right? But there's one caveat, big problem, right? How do you know? So I showed you this block diagonal plots, right? That seems to do the right job. But the question is, how do you know the subspace you learned is just enough? It's good. The dimension of the feature are exactly the dimension of the original data. This may be 10, this may be 11 or 9. How do you know that, right? The question is, is this mapping good? Does it preserve all the essential structures? And you can go back, right? Naturally, the only way you can check if Z is good enough, you have to reproduce X. Right? Now, let's restate a little bit more. We try to start with something very minimal, right? Start with our data. Nature doesn't know anything. They just have the data observations. Right? So then we go try to learn some features, sparse or incoherent, low dimensional, and we try to go back. We produce X such that it's very close to orienting. Question?
Just one clarification question. So what do you mean by saying that the feature you learn is white box? Because
it's a subspaces, right?
Yeah,
but exactly what they are.
But the current, without your system, it is still a latent space, and the only way we make sense of it is to tweak the Z and see what is the X. So in this sense, it's the same.
Yeah, say here with Z, we know the distribution of the Z in the hidden space, not the labels, not just random sample around every samples.
Okay, so you exactly know.
Yeah, we know the global structure.
I see.
Right.
So
even we can even parameterize them. All right, everything is subspaces. Geometrically, statistically, they're very many.
So you mean
we'll see the benefits of it.
So you mean the distribution is explicit?
Yeah, there's crazy implementations. Yeah, it can do many things. So now the question, just to state this question a little bit, right? It's just auto-encoding, right? We have those. We try to learn from X on multiple manifolds. We try to map the subspaces. Of course, the F and G, the mapping must be benign, continuous, isotropic, whatever we want, smooth. And we want to go back. At least, even we don't want the sample-wise go back, we want to at least restrict to each submanifold should be auto-encoded, right? There's many levels auto-encoding can pose, right? But there's a caveat. If I'm dealing with multiple subspace, multiple submanifolds, right? I map to multiple hidden space. If I want those features to be orthogonal, I have to choose ambient space at least larger than the sum of individual subspace, individual submanifolds. Hence, everything has to be hidden. Right? They're all distributed on the low dimensional manifold, even after compression. The data actually sits still in the feature space, lies on low dimensional subspaces. But nevertheless, if we can make them linear, we know they are. We can chase where they are. right? So that's what we wanted to say. So one way to fix this, instead of making them not hidden, we enforce what we learned there is structured. We can find them. Nothing is new under the sun, okay? Despite whatever, but we try to convince you otherwise, right? We have been doing this for 100 years, right? The same problem, right? If my original data is already on the subspaces, this is exactly called PCA, right? Everybody knows this. Oh, by the way, all right? So if you have multiple subspaces, we call it generalized PCA. That's my second book. Of course, those are, but they're not very useful, right? They're very idealistic. There's no data, no real data are really linear, right? Sound, music, they're not, or that the faces, they're not, right? So we have to deal with the data actually lies on some nonlinear manifold. We have to map to a subspace, linearized. Actually, that is the first paper. That's exactly auto-encoding. It's called the nonlinear PCA. Probably many young kids don't even know, right? Where auto-encoding come from. It's exactly another name for nonlinear PCA. Right, the Kramer's paper, 1991. Of course, Hinton follows up. There's a 1993 paper, right, about auto-encoding. So now, actually, the most useful case, this is just one manifold, right? The real data, ImageNet or CFAR are 10 manifolds, maybe 1,000 manifolds, right? This is a more useful case, at least. We have to dealing with data lies on many, many submanifolds and map them. Well, how do we do that? Maybe we can learn something from the simple case. That's what we always do. That's how we approach science, right? Start with simple case. If we cannot even solve the simple case, we forget about the harder case, right? So this is simple case. We know how to do it. If the data is already on linear subspace, we learn a projection that then we lift it back to original space when we minimize difference, right? Everybody in this room should know this, right? This undergraduate linear algebra. There's an almost closed form using SVD, thresholding, we're done. So now the problem is, what do you do with the data as a nonlinear? That's a trouble, right? X is nonlinear. What do you do? Well, you can at least pretend to do the same darn thing, right? We can pretend. We always do that. Let's do, learn some nonlinear mapping. I cannot count on this mapping definitely cannot be linear. I have to learn some nonlinear mapping, map the data to a subspace. Then lift it back through some nonlinear mapping. Hopefully, if I'm lucky, right? The X hat generative, this form of sort of auto-encoding. X and X hat are very, very close. There are two major problems. One is what is the F and G? You don't know the distribution. How do you decide on F and G? Of course, these days you can say, oh, let's try some neural networks, right? But theoretically, there's bigger problems, right? I have to answer that question. Second, but this is actually turns out is not the bigger question. The bigger question is, unlike the linear case, we know precisely just to measure the two norms between the reconstructed X and X hat. In the nonlinear cases, for data like images, what metric, what is the distance between them? Computer vision, image processing has been working on this problem for 30, 40 years. They're still debating what is the right metric. I'll give you a very simple example, right? The same image, if I shift to the left by a few pixels, the L2 norm changed dramatically. But it's the same darn picture, right? The measured distance should be 0, but L2 changed dramatically. Now the same picture at the same position, if you blur it, okay? Everybody see, oh, this is really likely, right? Compared to the accurate image. But the L2 changed very tiny. You can do that. Hence, this is a whole business, right? 30, 40 years of studies, trying to image processing, computer vision, computer graphics, all trying to say what is the metric on that. Of course, I mean, since Kramer, people say, oh, how do we do this? Of course, we don't know the manifold, but we have to, right? We have to start from somewhere. The one thing we can start is that let's guess that maybe we know how the data was generated. Maybe some nature, the statistical nature, how a lateral image was generated. There's lots of study goes into that. What is the lateral statistic of images, right? In 90s, 2000, right? We have to assume the data is generated somehow with some generating model. Now, here comes the big question. Image is million dimensions. And those distributions are degenerate. Even they're not degenerate, computing the maximum likelihood is not tractable. It's NP hard. All right? Sample, if you don't have closed form, the sample goes to exponential in the dimension. Forget about it. If you know the generative model, computing the posterior, forget about it. Then what do people do? People prospect, right? Well, they optimize some bounds, some variational bounds. Hence, variational auto-encoding comes along, right? We cannot do the precise thing. Let's just pretend we do some bounds. Well, it turns out that the bounds, the variational bounds, is not computable either. What do people do? Well, let's get some surrogates, right? For different data, different cases, how they're generated from nature, the hidden space, what kind of, what do we try to match with the surrogates? What the posterior might look like, independent, disentangled, God knows what, right? That's why there are gazillions of papers out there. Because everybody can come up with their own surrogates, claim it's better than others. Okay, on some other data. That's it. So after a while, people give up, right? It's not that people, actually, it's not just the VAE, even before VAE, people actually try, the generative models to do this, right? And there's a gazillion papers on image processing. Now, after a while, people say, let's give up. I don't really know the generative model of natural images, right? I cannot play with any surrogates anymore. Can we just learn generative model from the discriminative approach? So to tell the real image from the fake one apart. Actually, Tu Zhuowei is the first person to come up with this idea. His 2007 CPR paper, the title is precisely learn generative models from discriminative method. Okay. Why he gave up? He actually has very working examples, texture synthesizes. It's too darn slow, right? At that time. Of course, after a few years, the good fellow, those guys make this popular because they have faster GPU stuff, right? They can, so the idea is very simple, right? I have a generative model, X, how do I know X hat and X is close or far? Well, I try to learn discriminator. If I can tell them apart, maybe I can, this some kind of pseudo distance, right? And then actually, good fellow followed with this as a minimax game between the generator and discriminator, right? Turns out this is a fake game, right? Because it turns out this is just minimization. This is exactly minimizing this max mean is mathematically equivalent to minimizing the Jensen-Shannon divergence. Here is the tricky part, right? Haha, this is great because see, the good thing about the Jensen-Shannon is that if you have degenerate distributions, two Gaussians, right? For example, they don't have the same support. KL divergence is not defined. Okay, guys, forget about it. Mutual information, nothing is defined. Jensen-Shannon is. But it doesn't have closed form, not even for Gaussians. Another thing turns out, it is defined, but it's extremely hard. It's actually intractable to optimize. Why? Because it's exactly like L0 norm. Right? Only when these two supports overlap, it drops. Okay? When they are not overlapping, doesn't matter distance. It's just function like L0 norm. Well, I just finished the 700-page book, right? Writing how we should, how hard to optimize the L0 norm, right? So you have to relax, right? You have to this is impossible to optimize. But yet somehow everybody celebrates, right? GAN is a universal diffusion learning machine. Yes, it is, if you can solve NP-hard problem. It's almost like you don't need this book if you know how to solve any sparse representation. Go solve L0 norm minimization. We're done. It's tautological, right? You don't make any progress by saying something like that, right? Computational. So in practice, what do people do? Well, this is not very computable. Let's approximate with the W distance, right? Earth moving distance. That relaxes things a little bit. But unlike this looks like this, right? W distance looks like this. But don't be fooled by this, right? This is unlike L1 for L0 because this has a lot of expectation outside. Right? This is not computable either. So what do people do? It's approximate again, right? For practitioners, let's approximate this with some neural networks, optimizing here, right? For theoretician, even W1 distance between two Gaussians, there's no closed form formula. Meaning that to any computation, you have to sample, you have to do numerically. Even for Gaussians, for God's sake, right? There's nothing you can analyze theoretically. All the people I know from MIT, Asuma's group, and also David Shea's group about GAN, what do they do? They further relax this one norm with two norm. They started with W2 norm. Why? Because finally there's a closed form for Gaussians. They can do some analysis. Again, we just write a 700-page books, tells you how big difference between L1 norm and L2 norm in high dimensional spaces. That's why the theory has nothing to do with practice so far. Right? You are embarking on the wrong trees. So it turns out that there's something you already have, right? The rate reduction is precisely a closed form distance between two non-overlapping, even big mixture of Gaussians, subspaces. Algebraically, geometrically, probabilistically, they all make sense. It's closed form. It's computable. Why not use it, right? So this is just the whole minus the sum, the whole minus the parts. It gave you the distance between Gaussians or subspaces. Now, don't let me fool you, right? This is the distance on subspace Gaussians. The data do not have subspace Gaussians. X are not, right? Our original problem is about X. I got stuck on this problem for about a year. I don't know how to get out of this, right? We have a very good measure on Z, if we can make Z good, right? Subspace, right? Those are the closed form Gaussian. But I want the distance between X and X hat. How to get around this? Because everybody, the whole literature, whole community is trying to guess what X hat, right? All kinds of distance there. Turns out this is after I figured out this is actually something we have to kick out. I kick myself out about it. Let's just recite this. We try to learn, right? We try to map the manifold to subspaces. We want the subspace to be orthogonal. We want each manifold to be auto-encoding. Now here's the biggest question. Do we ever need to measure in the data space? About intelligence, about learning. All intelligent beings in the world, do they ever measure anything in the data space? Absolutely not. We never carry a ruler in your pocket every day. Say how big this thing is. Is my estimate wrong or correct? Do you ever do that since you were kids? Never, right? Ever. But how the system does that? How we do that? We never ever measure in X. Then why we study all the distance in X space? Even ants don't do that. They're smart enough doing things we're not doing, right? Idea is very simple. The nature already figured out. Everything alive, everything intelligent is a closed loop. Only one function consistent to ourselves. Right? So you don't, if you want to measure, want to tell if X hat, how close they are. You don't measure them directly. You cannot. Nobody does. You measure the feature, map them into an internal map feature again. You only compare the feature of X and X hat, Z and Z hat, how close they are. That's exactly the notion of control, feedback control. Right. So you want to make sure my regenerative data and the real data, there's no difference from whatever I can observe. I couldn't care less of this. So once you realize this, things become very, very simple and tricky, very simple and easy, right? So we don't compare X and X, we compare from the same map, feature map F, that compare X. Then in this Z space, I have full control. In my brain, I control everything, right? All the resource, every distance, everything makes sense. Statistically, geometrically, everything makes sense, right? The distance even become closed form. This is all I care. The number of colors, number of spheres I pack, right? Which one is better? The whole is sum. Right. So everything here is closed form, and then the sense now the point of this encoder F plays two roles now. Right? You can call it the encoder feature mapping. You can also call this is a sensor. If there's any difference between the real data and my replayed data, I should be able to tell them apart. Just like artists, right? We paint, we draw something, right? You always constantly compare with what's in your brain, what the real data is. But all see through your eyes into your brain. Whatever you can perceive, you tell the difference. And what if you're colorblind? By the way, we're not modeling anything beyond the infrared, ultraviolet, violet. Why? We couldn't care less, right? We only model what we can perceive. We tell the part there. Then that's what the sensors F does. And the G is really the decoder, right? We try to reproduce X hat so that it's close enough. F cannot tell them apart. That's all the G has to do, right? It's actually decoder, but also it's a controller, right? Why it's control? Right? See, this is my target. It's solid data distribution X. So the decoder is from the whatever the feature space. I decode the data X hat, right? X hat is the blue curves. There's a difference. The decoder is trying to control, to reduce that difference. That's exactly our controller air conditioning is trying to do, right? Control the temperature so that there's no difference, I can tell. G is a controller. And that's exactly, so if the blue lines and the black line overlap, self-consistent, the loop reaches a fixed point. The temperature of a room will be precisely 75 degrees. Right? It's a natural, this is a real game. This is not a fake game. This is exactly evasion pursuit game. And against manifolds against manifolds. That's it. Right? And you actually end up with, combined with MCR, this is actually trying to make the features expand. This is trying to make the feature compress. Right? And also this behind the balance, right? You can think about the sensor trying to tell everything apart if the resource allows. But G says, no, don't do that, right? I only want to pay the number of bits. As long as you within epsilon, you cannot tell things apart. Right? It's really trying to achieve a natural balance between these two. Right? And it's a multi-class. If you have multi-class, you're just using the measure delta R to measure, right? All those quantities just measure this configuration, right? The difference between this black lines and those green lines. All the cracks in between. Nothing else. Absolutely nothing for you to decide. Okay? Everything's counting the bins. No heuristic, no weights, no free parameter for you to do. Absolutely not. Right? So if you don't, you treat all the classes as one class, fine. This is a binary case. Right? Just the fake one, the produced one, the one. And this is very different from GAN. It looks very much like GAN, a binary case. But this is measured the distance between two distributions. Give you much, much more richer information than just the binary bits. Very efficient. Now, does this work? Yes. Right? Once you have the close, it actually works magically. Right? So now the question is that kind of this formulation, right? Everything is bin counting. Absolutely no heuristics, right? And everything is closed form. And the self-consistency, if it reach optimal equilibrium point, it achieves the closed loop consistency, right? And after you learn, if you converge, you know what you learn. The feature become orthogonal subspaces, right? And suddenly, there's a lot of those. You don't need to specify any prior, any circuit. They're all gone. You don't have to do any distance between x and hat. All the bounds, KL divergence, Yancey, Shannon, W, they're all gone. You don't need any of them. You don't have to approximate them. You don't have to compute them. You compute what you want, the distance you want. You control the structure you want, right? And all the algorithms, the results you see here, absolutely, there's no heuristics, no engineering tricks. We'll try to make the point. I asked my student to make the point. For all the data sets of images we can get our hands on, and let's just see far as the D or the thing. Using very much the same network. We're not customizing the network for anything, okay? All the data, doesn't matter high resolution, low resolution, larger data sets, smaller data sets, use the same darn parameters. We're not customizing anything. No hammer parameters. And there's no other regularization, no heuristic, no engineering tricks. Actually, this is an exercise in my course now. All 70 students did this absolute problem. And you can see this started to work like a magic, right? So you can compare with GAN. This is all fair comparison. By the way, if anything unfair is unfair to ourselves, we use a much simpler network, or use even less data to train. Okay, if there's any differences, it's actually unfair to ourselves, right? But you can see that in terms of quality, and the VE doesn't really work for qualities, but you have to do some tricks to make it look good, right? So at least for MSSPC far ImageNet, you can see things start to work. And also, not only that, you learn more, right? It's simpler, but it's actually learn more because different classes, you can see all the data sets and the subspace structures start to pop up in the features. They become subspaces. You can sample them, right? You can model each class as a PCA. You can compute the PCA. You can sample along each principal components, right? And compare with other GANs to control the class, right? AC GAN and by info GAN. I mean, they actually mix up things. They are not intent disentangle, but actually this one disentangle everything as also subspaces. And also, we compete on both fronts now, right? So this model we learned is both discriminative and generative. They're subspace. I just do a linear subspace classifier. So you can compete with the best generative model, compete with the best discriminative model, which are the VAE. VAE are good at the discriminative. GANs are better at the qualitative. We compete on both sides. Turns out the lesson we learned, the best discriminative model is generative. Best generative model is discriminative, just like our brain. Right. And you can go from one subspace to another to see how digits translate. And here's another thing, right? So you can have different orientation scale. The PCA just pick out every single one. Scales, orientation, they're just automatically become different PCAs. Everything becomes statistical. And this is the principal component for CFAR 10 classes, right? Each class is a subspace. Then we pick out that subspace. So now we don't go back to trace which image generated that subspace, that direction. We can regenerate image, right? Along that direction. Those are the images you saw. Along the first principal component, second component, there's a regenerated image. They're precisely statistically. So in machine learning, there's a lot of debates, right? It's very possible to disentangle. Disentanglement is trivial. Different classes get disentangled as different principal subspaces. Different attributes, statistical attributes, gets disentangled as different principal components. Everything is statistical. You don't, it's only hard. You try to guess those surrogates, which should be dependent, which should not be dependent. Here, there's no guess. Data stipulates everything. The distribution of the data tells you everything, right? So for example, face, if you can treat all the faces as one blob, one subspace, right? We learn. Here's what you get, right? You get some PCAs, big subspaces. Then we pick, right, the nice principal components. Let's sample along those. Unlike GAN, right? We'll pick two examples, see how we get transition from one to another. Here, we just sample along one PCA, everybody wear hats. We sample along another PCA, everybody change hairstyle because it gets linearized. The distribution gets linearized, aligned. Right? It gets distinct. And this is also pose, right? So you can see this is the face generated. This is we're not, of course, competing with those big firms, right? You know, company that will get the but every time, as I said, this is very, very tiny, right? Very, very strict data sets. And this is ImageNet, just to show you the idea, right? Again, not only we can generate the data, and we actually learn better, right? We can see the features, the block diagonal structure, the feature hidden space, they're not hidden, right? They have structures to emerge. And we're not the best. Of course, we're not competing with low GAN or the big GAN, those are things, but we're close, right? On the data sets that the same turn out, same data sets, we're close, we're top 3. Right? Very, very simple. Also, we're not, there's no tricks. The thing is very stable. There's no mode collapsing. You can over-parameterize your width data. Turns out everything is statistical. Just have a bigger batch, you get a very beautiful phase transition, right? As long as your batch size scale proportionate to your model width, everything converge. Right. GANs are very finicky to train, you know, engineering tricks, no, nothing. Right. So everything statistical becomes. Right. There's a lot of application study, you can check our work, right? So because of our first rate reduction paper came around, people are questioning, is this going to be useful, right? This is going to guide practice. So the second part is really try to convince you that, yes, it is. It actually go beyond. Right, so to summarize a little bit, we actually propose, right? So you can see now, deep network is actually a segment, right? The discriminative part, encoding, and the generative part. They are actually two segments, open segment of a closed loop systems. If you wanted to train them independently, fine. You need a lot of input-output data. If you want to use them as an open loop, control have learned that lesson 70 years ago, right? Don't do that. Open loop control is expensive, not adaptive, not robust, right? Using everything in the closed loop. And also, this actually unifies all the discriminative generative models in this. Right? The models you learn are both discriminative and generative. They actually start to couple with each other to check if they're good enough for each other. Right? All you need is this kind of closed loop form. And really the measure is just bin counting. Absolutely no other old words, right? How many loss functions each papers, right, these days? And nobody can explain what they are, right? Different ways I try. Here, there's no weights. Nothing for you to decide. Just compression, linearized, right? And you use a closed loop to achieve that. It's a real game. Right? And whatever you get, the object function, the architecture, and even the feature you learn, it's white box. Right? And this actually opens up, if you know, for people who are interested in mathematics, this just scratch the surface, right? This is some of the hardest math problem comes to pop up, right? When this is the game, right? When this have an equilibrium point, we have some recent work, I'll show you that. In fact, in terms of control problem, if it's manifold chasing, right? It's infinite dimension, theoretically, okay? When this have an optimal solution, I don't know. You know, we're not just learning the manifold, we're also trying to linearize it, right? This is what I call the passive manifold learning. How do we do that? How do we control the dynamics? When you can succeed, when you cannot, we don't know. Right? And it turns out, even you restrict your data subspaces, when the data distributed in each subspace the ratio becomes a maximum. Turns out, even in this restricted case for us, right? We're dealing with manifold, we're also even be able to change the support. Everything restricted in subspace. Just thinking about when the distribution become optimal, the map, the whole and the parts become the ratio become largest. That turns out it's called the mother of all inequalities in mathematics. Called Braskamp-Levy inequalities. All the inequalities you're familiar with, Young inequality, Cauchy-Schwarz, they're just special cases. And it turns out actually has some papers 10 years ago, precisely studied. They don't even know when the maximum can reach before that paper. Actually, they showed that, you know, in that paper, that showed that when the data in each subspace precisely has a Gaussian distribution, the ratio becomes maximized. But they don't know the result, it's non-constructive. They only know it's Gaussian. Okay, here we have to compute it. And how do you know this no overfitting, underfitting? In fact, in our experiment, we never see underfitting, overfitting. But there's no proof. The only case we can prove, we just submitted to NIPS, is when the origin data is already subspaces. Turns out, yes, this formulation, the game theoretic formulation, precisely gave you an optimal solution. And also, all the dimension for each subspace is correct. There's no underfitting, overfitting. We're going to push all the subspace to the rightful positions. This is the only case we can prove. Sort of a sanity check, right? In the simple case, the formulation makes sense. Actually, it's not. Turns out that the equilibrium point is not a Nash equilibrium point. It's a Stackelberg. It's a sequential game. Right. So on the practical side, there's a lot of things you can try to do. Right? How do we scale up to thousands of classes? Right? And this is actually turns out that this is supervised. Right? We know the class labels. What about unsupervised, incremental? Right? Does this say other things? How do we replace the network with white box? What about other type of structures? So it turns out that the closed loop is very, very magical, right? We know that open loop systems, if we train new classes, new tasks, we experience catastrophic forgetting, right? If you learn 10 classes, you learn 11 classes. You retrain it with new data. Without the old data, you forget. That's an open loop system. The closed loop never forgets. Right? So here you can train. Also, the key here is that you have to know what you have learned here. If you know where the old things you have learned, features, you can protect it. All your brain has to just make sure it gets protected. When you learn new classes, representation for new data, those old area neurons gets protected a little bit. That's all there is. That's why you need a structured representation. You cannot learn a hidden space. Don't know where the data has gone, the feature has gone. So once you do that, you can formulate this as just a minimax game with constraint. On the old memory gets preserved. New data gets incoherent, right? Suddenly you see, right? Those are much more complicated method, right? Compare, this is just simple closed loop. Suddenly it starts to work, right? You don't ever have any forgets. You get double digits improve many of the even simple data, right? People are still struggling with city. Now in SNPs, MNIST or CFAR, they are very much, and also even this tiny image net were actually very, very high. There's no catastrophic forgetting. It's something very interesting. If you show the network the class it has seen before, the model gets reconsolidated. You don't have to tell the network it's a class it has seen before. It automatically knows. Something very, very interesting. We don't know why. So just like a human being, right? We saw something we have seen before, our memory gets better. The closed loop has the same phenomenon. What about the unsupervised? Here's still one class at a time, right? Or if I only have one sample at a time. Same darn story. Just treat every sample as a new class. The loop will eat it, right? And this is the latest paper actually we wrote with Yang Kong. I mean, I think his group is converting to this framework, right? And you will only have to treat every new data as a new group. That's all. This is all its argumentation. Its own group. And the loop will stop. And it's something very, very magical, right? It actually turns out it works better than the class-wise incremental. We don't know why. Just one sample at a time. The system, once it loops up, right? The auto-encoding actually is better. See, the class block background shows up also automatically, without any class label. Just one sample at a time. Right? And also you can see compare TSAE, right? To visualize other local weeks too. This is the latest structure for unsupervised learning, right? The feature we learned is very structured, very thin. Even one-dimensional structure gets preserved in features. We don't know why, but they're just strikingly structured. All the structure just emerge without any supervision, just compression. Incounting. Right, with a closed loop. And it turns out, this is what people see in monkeys' brain, right? That's exactly, see, the monkey brain sees the three categories objects, the measure, the response in the IT cortex. And of course, monkey is never supervised, right? Never class supervised, incremental, just one sample at a time, right? It just automatically associates with objects. Right here, you can see the feature we learned, the block diagonal, looks just like on monkey. We don't know why. There's a lot of collaboration going on right now. Right? So this is actually a series of papers, so capture. We actually did all this, looking at the issue with degenerate distributions. When we didn't high-dimensional data, the distribution is always degenerate, right? Maximum likelihood, care, divergence, they all doesn't make any sense. Okay, they're not defined. I don't know why people are still writing papers about it, right? Every formulation of lift start with scale divergence, mutual information, and maximum likelihood, pretend as if they exist. No, they don't. You cannot compute them. The best you can approximate them, right? And you have to be clear what you have approximated. And actually, we learned that lesson about 15 years ago when we do image classification and segmentation. You cannot treat those distributions. You have to use compression as a tool to unify the degenerated and non-degenerate distributions. Right? And we will apply the classification and clustering. And suddenly we start realizing compression is also works. In representation learning, only you have to use nonlinear mapping, which can be manifested as deep networks to achieve that mapping so that you make your data subspace or Gaussian. Then you can represent them in a very structured, compact way. Right? And it will start to work in all settings, discriminative, generative, supervised, incremental, continual, or unsupervised. No difference, the same framework, right? And this is some book I wrote. I brought a copy for Eric. And by the way, something really remarkable. I encourage everybody, I'm giving talks these days, everybody go back to read this book. This is the origin of AI, not the 50s program. Because in this book, we're going to precisely talk about every ingredient I've talked about. Feedback loop for learning, and compression, white box modeling for the brain, and game theoretical learning. Yes, he's the first one proposing the right learning framework is game. Actually, not the von Neumann game. Not the worst case game. Read it. Right, that's exactly what the reinforced learning people are doing. And also that the shifting bars is trying to generalize nonlinearity. Remember, at that time, even in linear system theory is at its infancy, but he's already dealing with nonlinearity. He realized for learning, nonlinearity is very, very crucial. He's trying to generalize the harmonic analysis to the nonlinear case. that he actually characterized brainwaves. He actually figured out why brain compute in frequency, not in time-space domain. There's a reason for it, right? So yeah, that's all. So basically, you can see that this whole thing, I hope this gives you an overview, right? We have to stand back to look at how intelligence may emerge, right? The necessary elements. And maybe, deep networks or some of the things are just one chunk of the element of a much bigger picture, right? Even everything I said today is only about the intelligence of individual agent learner. Doesn't say anything about the social groups, right? All the symbolic, logical, semantic actually has nothing to do with this level. In fact, deep networks has more to do with the Wiener's program than the 1950s, the artificial intelligence. It's precisely provide the interface to the raw data and the structure. Without that, we can keep talking about the symbolic computation logic for another 50 years without any progress. That's the true value of deep learning, right? This interface between the data and the structure you wanted. And we have to combine them in the closed loop to see the big picture. Okay, thanks.
For excellent insights in this presentation, and we will take a few questions, please.
Okay, the obvious question, thank you for the wonderful talk. So much here. But the obvious question is NLP first. It's for discrete inputs and outputs that we and how does it apply?
So there's a couple of things, right? So differently we tried. See, even the deep network, also that natural language also have structures which inherited, right? We don't know. I think one aspect of the intelligence is to figure out why natural language emerge. I think that's a different level of question. What we're saying today, so maybe the structure, the symbolic, the structure of the data. Now you have some views to build on top, right? Without the structure, the representation, there's no even starting point for symbolic. And nothing we can share, right? We don't even recognize the same class of apples, right? So that's one thing, but we don't know that. But the second thing is that since if you treat the language as self as object, just as signals, right? So I think networks also shows well, how to extract those structures, how to align them better, how to correlate, find the statistical correlations among different sets. That actually also played a role there. Another thing, you are the expert, right? I asked one of my students had a startup doing the English Chinese translation, quite successful. But I asked him, have anyone learned translation in the closed loop?
Oh, I can think off the top of my head.
Well, so let's give you a think, right? Maybe they're not. See, there's two things everybody should do. So loop is easy. If I only map from one style to another style, right? If I have for the same dimension to same dimension, the one mapping is easy, right? We're all mathematics, right? It's very, very easy. Just like style transfer, like cyclogram, right? So the loop is much harder. The nature is solving a much harder problem if you compress. One dimension is very, very, I want to reduce from millions dimension to a few hundred, right? Each class from, to a few dimensions, then go back. That's why the two things together is very hard. Self-consistency is trivial, right? I mean, one mapping. That's why in all the probabilistic model, probabilistic diffusion model, add a little bit noise, diffuse. Actually, that's a simple problem mathematically, right? Even the normalizing flow, if I just learn distribution in the same domain, it's actually reasonably okay. That's fine. But if I want to go, if the distribution is no dimensional, go find it and linearize it. That's much, much, much harder problem mathematically. Right? So for language, now another question is that if you want find something common, if you just translate it, that's just one mapping, right? If you are lucky most of the time. But if you really want to understand the grammar or meaning of it, there may be something hidden there, right? Our brain that's why we learn multiple languages. We have no problem associating them, right? But definitely we don't have a translation machine in our brain, right? We don't remember each of them and then translate, but everything should share something there. But what is that? I think this framework hopefully will provide more thought to it. You need to transcribe to it and then go back to it. Because think about each language is more like instantiation, right? There's an auto-encoding between there.
against that. But how we can use this to help with that, I'm not sure.
Yeah, I want to add that using a closed loop kind of analogy or metaphor, in my opinion, is one way of casting the problem, which is usually working well on embedding representation learning and all that. For example, maybe you can add that translation actually has two ways, right? Now, the machine translation and the human translation are very different. I can imagine machine translation could be done in a closed loop way, which is the mechanical mapping of source language target language. And right now, that's what's happening. Okay, you have a big kind of a transformer in the model in the middle, and I just do mapping, which does all alignments, representation, embedding, and that. That's not how human translate. That's why we say when, for example, I challenge people, you train a MT model, you get some data representations. Can you use the same data representations to complete another task, which demonstrates your understanding of the semantics? Most likely it's not. And that's because it's a dividend, but it's a cost you pay actually, or penalty you pay for end-to-end or close to
exactly.
And not trying to understand.
Yes.
So in a sense, I'm not ready to accept that you have one principle or a information-theoretic or a coding principle to define AI.
No, this is not a general.
Yeah, as you mentioned, for example, logical inference, symbolic inference,
yes,
and all that,
yes,
are not ready to be encapsulated in fact in this principle.
So there's two things, right? So one is that today we've only talked about the visual data, right? In fact, even the visual data we work with is just already, they should have a low-dimensional submanifold structure, right? They're actually already aligned. Right? So they're not like, transformer probably have to handle the alignment of the data. Here is a simple cases. The structure we're looking for is relatively simple.
I think the closed loop framework applies to all following scenarios in the effort. Why is supervised learning? That you have input and output mappings. Yeah. You can actually, in fact, in the original probabilistic inference model in Berkeley models, you have the generative model and the version model going backward. It's exactly the same thing, I'll say in the data center. The other scenario could be an auto-encoder where you regenerate one, that you have one thing and then you have the same thing in here. You basically reproduce like in your auto-encoder. Yes. But there are many tasks which are completely open. For example, when I translate or when I debate with someone, I actually don't know what he's going to say to me. Yes. I'm going to be completely open-ended, and my thinking and my encoding and my reasoning is going forward without a target.
Yes.
And I think that in AI right now, a lot of things are stuck in that area.
Yes.
How to actually build a machinery that is open-end and handling unknown things, and also without even getting a feedback when you do something. And how to scale that. Something actually is very interesting.
Yeah, I agree, but that's a task may be open-ended, but then the learning to do the task well can be a closed loop, right? That's why we even debate and we train. That's a game. Actually, you actually really do need to read actually this is actually one of the.
So I think maybe you can agree on the following. So learning, learn what is about learning representations. Right? You don't learn to solve a task. But that's actually
yes,
exactly.
That is a game. That is you have to learn that in a game. You have to assume certain adversarial.
You learn certain knowledge, just like a human being, you learn in college and certain knowledge, in this case, representation. But then, when you solve a task, there is a open space for you to
extrapolate.
And to innovate. And that actually leads to my second question, which is often downplayed in the entire field of machine learning and AI, which is the operationalization. Because when you solve open task, when you solve it, you need to have the freedom and ability to combine and operate optimize. So sometimes I think what I learned from deep learning, which has many negative sentiment to that, as a dark bottom, but one thing it did very well is that it is very optimizable. Yeah. That you add a component, you combine transformers, you put transformers upside down and form a detection or something. It allows people to compose and to synthesize, right? But on the other hand, statisticians and traditional machine people are very bad at that. They say, yeah, here's a loss function, here's a framework. You have a coding theory, you have compression theory, you have the probabilistic divergence model and so forth. And then you are, you just place a model and then optimize. But this don't work model and the algorithm. It's the whole work of somebody else's research, which is discounted.
I agree. See, you got something really right. The operational and compositional, which was precisely the strength of system theory, right? Systems is exactly about how system gets concatenated, right? Synthesize, parallel, loops, and so on. System theory is very good at, but somehow system theory in the late 90s get distracted. They care about system only when those components are transparent, are analytical, right? Which is a big mistake. Right? In fact, if you go to read Hinton, what Hinton was doing in the 1990s, late 1990s, system identification. You tried everything, right? EM algorithm, he was playing with those. And we have, of course, he gave up, right? Because then he just started to go backward to neural networks. Because that allows you more flexible to map in the input-output. Because you might get sick, even I got sick, right? Every time I have to write out differential equations. If you don't have a differential equation, you cannot say anything. Turns out that's exactly what you said, right? We have the deep learning actually made a very flexible toolbox for us to model, maybe operational, to model the system, model the input-output map. But still, it's a segment. We still need a bigger, better principle to how do we synthesize to build systems.
Actually, that's a word I had a debate in the past with someone, about the word attention. So if the deep learning model becomes small and now viewed as a component, okay, as a building block, and then the bigger problem needs people to even synthesize multiple elements on top of that and so forth.
Yes.
Do I do care basically even what is inside deep learning, rather than view it as just a little black box as much as I can destroy it, and then I worry about how the interplay. Because for example, right now we take medicines. Yeah. We take food. Do I need to even know what is in the medicine as much as it tells me that
that's something. I absolutely agree.
And also even I challenge also the so-called explainability. Actually, I have to be a biologist. So I know biology more than many other doctors. They claim that they are giving me something that is explainable. I said, really? Yeah. You really know that aspirin is acting on a certain molecule, control certain organ, and therefore cure me? They don't. Yeah. They actually are also
tested. Yeah.
They give their hypothesis, which is for the psychological comfort that they thought it is explainable. Yeah. But to a molecular biologist, that entire explainability is gone. Yeah. But I still take it. Just because it's empirically good. So now, if I'm a criticizer of deep learning, but I want to give the practical. What if that deep learning thing, for example, the word model, give me the good embedding of the words, of everything, then I will use it as the building block of my next thing. That
absolutely
be totally fine of not asking for why word is just repeated.
Absolutely. So there are different layers. One is to use deep network. For example, any of the segments, FL or G, generative or discriminative, they're themselves already very useful. But what I'm trying to say here is that we still need to understand what function they're to achieve. So we also potentially have criteria to say maybe we can improve. Even BERT maybe give something we can already use, but there may be things we can also further improve. What we want to often, or compare with potentially better, if I want not just to synthesize the signals, I wanted to do other tasks. I may want to know what I have learned, right? Grammar, which part learned grammar, which part learned the meaning, things like that. So one thing we learned from this is that precisely the system is only trying to represent the data. It doesn't really quite tell you want to use this for classification or for other tasks, right? So that's why it's shared here. This is a simple example. I'm not saying this is solve, all the problems.
We have another, slightly philosophical thing. If the task is higher level and compositional, then do we even care how good the embedding is to a certain degree?
No.
Right. So then.
But we need to understand theoretically how good needs to be. You know what I mean? Give some kind of quantitative, right? In fact, this is one belief. Why we do things in closed loop in control? In fact, control always knows. There's no way you can identify any system precisely, right? That's why nature already figured out, right? We can never identify this, but as long as in the neighborhood, right? As long as the error is reasonable, we can correct it.
Yeah, but
right?
then,
So you need higher level. First of all, you need to understand how close those system gets identified within certain neighborhood of the truth. Second, all control theory says within that neighborhood, then we can guarantee a closed loop system, the fixed point algorithm, give you the correct solution. You know, no disaster would happen. Yeah. So that's kind of guarantee we need to build for that
definition is very tricky, right? Yeah. Embedding does not have truth. It's basic judgment. We usually need an external kind of auxiliary job to determine the quality. Right now, which is classification. Yeah. Or I often challenge my colleagues in that case. Do you really care that a particular object condition, needs to be very, very accurate in order for me to do other things? Like you yesterday gave an example over the weekend that you have this impressionist thinking that in the middle there's a color block, which you have no way to classify it. But for people who stay afar, they will know it's a locomotive and something else. Right? So in a sense, I challenge the very kind of design of the experiment, how we even qualify, the quality of the representation or embedding in the middle. Without the context of the bigger data, my context will be seeing understanding. Then do I need to even know everything in the pixel level? Earlier on, I also had other debates with people. I say, if you are not doing Photoshopping, why Photoshop? Why do you even care about pixel level classification accuracy? You don't care because that's not needed. We human beings, when we recognize objects, sometimes I don't actually see that. Clearly, I can still recognize it's a horse or something. So that's actually the challenge right now. We actually have the right framework, even in evaluating, that lower level.
Eric, you are absolutely right. So actually, I'm writing a position paper. I'll send it to you. All I'm saying that today, even the past 10 years, even what we did today is according to Wiener or the framework, still at the individual low level signal data structure level. Honestly, nothing beyond that. On top of that, really how language evolved, symbolic, what you say, that the parsing the scene, even causal relationships, even logic arises. That has a lot to do with intelligent beings to interact, social, communicate, transfer knowledge. That level, honestly, I don't think we have anything, except that we can manipulate, use a neural network to manipulate, transform from one domain to another domain, to learn some useful input-output relationships. That's about it. But in terms of really they're already good structure. Actually, neural network, to give credit, right? They can capture good structure already in those data. But whether to the extent of why the structure emerge, or what there's something intrinsic behind it, we're nowhere near to get those things at this point. I'm not even claiming even this framework. But there are something by the universal about closed loop. There are two principles. Why is it? You can think about the closed loop is kind of very universal in nature, right? The brain memory forming, the muscle control, even DNA, right? RNA to DNA. It's called transcription. It's a closed loop transcription. So this is sort of a universal structure, I believe, is nature figured out how do I copy one thing to keep what's essential, what matters to me, so that I encode what is essential and in a very compact structured way. And so I can pass it on or can use it later, right? So this kind of, this closed loop, how do we transcribe those visual data from different levels? Maybe it's a loop after loop, right? Yeah. From, low level to higher level, even from outside the world globally to that. So there's maybe multiple layers of abstraction to distill the information in this framework.
That's what happens for dynamic systems.
Yes, systemized transcription. As I said, system people has the right framework to study those composition, study how the complexity is dealt with, but they really distracted in late 90s, right, to just working with analytical form. They really didn't see the computation. A lot of things, just like Hinton did, right? He didn't try the system ID, right? Yeah, one of the things that he didn't work, right? He wrote a lot of papers about it. Remember, then he didn't give up. Let's just give up. Let's just do the system ID, use a neural network, right? Try to map even use a black box, just make the input output good enough, right? He actually embarked on that. He benefit from it. Like this is exactly what the system people, unfortunately, it is a system, but they don't want to treat it like that, right? They don't want to study that.
I remember there was a small debate in one of the, I think the intelligence, auto-encoding conference, trying to establish connection of auto-encoding system to like the infrastructure at. Yeah. And again, the moderator was trying to help me bring my work to the statement. He asked the following question: what is a system? Because I branded some of my work as system engineering. What is system? Guess what? There's a whole lot of answers which is kind of entertaining, right? Some might say system is basically within and also the environment, and because it's a system, yeah. And then some people say system includes social feedbacks and so forth, and then so let's try to get philosophical. I say, hey, what I hear is that system is a universe. You don't define a boundary of the system, then everything becomes a system. It couldn't even start a intelligent conversation because now that everybody claims that we system machinery. Everybody, but all the people who never write a code in a system, who never actually tune a machine, call themselves system machinery people. Yeah. I'll say, oh, you are giving me all of my job because I thought I'm unique. Now you are actually saying you are doing the things as I do. That's actually very interesting, right? So I think that what's needed right now is some kind of a boundary and a clear definition. You have to have multiple areas, but you need to also know that there is a boundary that you are crossing the area and doing the other. But I think what just raised by E on the system people doing something analytical only, not computing, is probably a consequence of that lack of boundary and respect of boundary.
Exactly.
They thought they are doing the system, but they never touch the system yet.
Yeah, well, the system can mean different things, right? So that's it's not just something you can write on different equation in the system, right? Yes.
And the world becomes too generic, and it becomes a universe, and the world is not even informative.
Yes. So I mean, that's why Harry Shang and I were writing a paper together, trying to do sort of position paper, perspective paper. We're trying to put some of the ideas together. So the one thing common I had with Harry Shang is that we are both trained as a control. We both study automation, or we're undergraduate student. We actually, that's why we started collaborating on some of the things. So we all realize that even so reinforced learning using this framework, but this is also, you can see the optimal control uses exactly the same framework, right? What we think answer your question of system, I start to believe that at least in system, there's a definition of what we mean by quote unquote system is that system needs to be autonomous, right? So basically there's no, except its own resource, its own objective, right? It should be autonomous, right? It should take nothing outside, only observation from outside. Then there's this decided by its action, right? Its action and all defined by its own internal objective and internal resource.
That's always a very, very important and interesting question. When you say system become autonomous, I still don't see right now any even thinking about how a piece of code can autonomously enter a computer, load it itself, and start to train. Because otherwise, if you talk about a system that is only software and no hardware, that's not a system. Yeah. And we human being has the brain, but also have the limb and the body. So therefore, we enter our code into a body autonomous.
Yeah. So, well, you can think about it. The system is not that self-closed, but it actually has a clear interface to the.
I think people probably went too far in already without even some basics. How to even put together what it takes a piece of code to self-load it itself. Yeah. Solving that basic thing before we talk about even the first group.
So I really I should try to read the Nobel's winner's book, where he has said that there are two characteristics about something you can call it alive or intelligent. One is that the ability to learn. The second ability is to reproduce itself, right? So that's the definition, universal definition of something alive or intelligent, right? So
we studied that.
right. So if the code will become alive, which means first of all it can learn, it can evolve, adapt, right? You can think about the loop sort of doing that, right? We learn from reinforcement learning, so kind of. But the loop doesn't reproduce itself.
Yeah.
We have to put itself for it, right? So for this to become alive, it has to somehow reproduce itself.
So yeah, let me be very honest here. The reason I raise all this is because I believe it is impossible. So I want to actually reduce the goal to something that is very, very optimizable. Because I don't imagine a paragraph reproduces that ever.
Yeah.
Okay. And therefore, building series on those kind of things becomes a fantasy. It's more like going back a bit and maybe try to break the problem a little bit closer to what is really feasible.
Yeah, the world has very different problems, and a lot of things we don't need intelligence. But I think if a lot of the framework we're trying to build, I think it's probably for people who are interested in really robotics, probably need to think about those kind of problems. Right?
Yeah.
Robotics, I mean, the individual agent needs to be very, very autonomous in the environment. Second, that maybe in the future we can want a robot to build themselves, right? Reproduce themselves in some way. Probably. And also the one thing got us very interested in this kind of problem is that I work on computer vision, right? I'm very frustrated with robots, right? Because see, all the robots go to the room, scan, right? Everybody's doing some like demos. I have another little robot. I come to the same place. I have to scan again, right? And how do they share? Human, we use symbol to share, right? If I'm in this building, ask where the bathroom is. You can draw me a very simple. I will never get lost. How in the world? I mean, robot needs to communicate at that level, right? Few bits of information. That's it, right? So all the knowledge gets shared. But right now, it's just darn point clouds, a mesh, a voxel, right? And then let's just align them to ICP. And Jesus, that's just unbelievable.
There's a technical question here, where to start, right? Let's say we even simulated two digital robot package. I think that task should go first to the computer side.
Oh, in the simulation.
Yes. I don't think it's fair to ask robotics that we as a computer science haven't figured out. We already asked the hardware. That's the whole point.
I agree.
The blame is like the other side of this and that. I actually want to shift the blame for ourselves. I'm always a criticizer of ourselves. I think the we as the AI people as statistician didn't do enough our own job in giving people tools yet.
Exactly.
And that's actually I don't see effect in our in Europe and
in fact, even the robotics people are learn big lesson from, a lot of things you can learn from simulation. If you do good simulations, right? A lot of things you can already solve your 90% of problems. If you cannot learn the direct control with a well-simulated controlled environment, how in the world do you play with the mechatronics, right? With additional layers of complexity or uncertainty, right? So this is actually very, very good. So one thing I can tell you a little bit of why, even we consider this. I got stuck with this big problem to compute to compare X and X hat for about more than almost a year. I don't know the solution. But I do think that the thought you put there is very, very useful. We need to do a lot of thought experiments first.
And also
right?
Into for example, whenever I hear people say reinforcement and so on and so forth, I actually was turned off the safety control because there are so many little things inside reinforcement, which is not just the element equation and the policy agreement.
Yes.
Okay. There are a lot of designs of encoding the action.
Yes.
Right. Encoding, maybe even not. I'm not talking about this embedding. It's real kind of operational encoding of the reward functions or the state action mapping here. Many people who are in reinforcement who claim to do reinforcement don't even know this terminology.
Yeah, so that's what we
exactly.
So
this is a problem. They over corsify.
Yes, that's what the problem is. They don't appreciate the actual computation or implementation of even the component. That's really the mistake. The control system people made a mistake. Right, and so actually that's why this is a figure I draw with Jitendra Malik, Shankar Claire. We actually did a course called the Integration of Perception, Learning, and Action. Right, so this is I did a little survey really about optimal control and reinforced learning. What is similar, what is not, right? And there's a whole talk. If you want to come on our website, you can say, right? It precisely tells people, control people, what are you guys are missing? Okay. you talk about encoding, right? How the high dimensional to low dimensional embedding, and also even the lack of analytical solutions, right? Modeling of the system, but RL is trying to model that. Control defect. Yes, it's under a similar path optimization principle, but the implementation is very, very different.
Another difficulty I run into is getting students here and then talking about you right now. No one wants to spend any effort on data. They thought I'm this noble person, some slave to prepare data for me so that I turn the key and run the experiment. Again, data processing is also part of machine learning and AI, but nobody wants to do it. They thought it's untouchable, and therefore, so in fact, that probably is equally true in computer vision. Computer vision basically, this whole area is led by data. ImageNet basically dominates maybe 90% of applications in the whole field, but the ImageNet was prepared by someone. And it's actually really serving your goal. Do you really need that data? Right? That's a problem researchers should ask in the first place. We human beings, as a human learner, we prepare our own data. But we not actually, when we become old enough, we prepare our own data. We know what to choose. And right now, I think that this whole field in research is reliant on suppliers of data. To the point that some of the data was itself synthesized by another experts. So these are the issues I wonder, for example, exactly. The whole framework right now, is that helpful to even shed light on how data can be processed before even they enter any system?
Yes. Right. Yeah, I completely agree. I mean, this is just to ask us a question: what do you really want to learn, right? What is the target of learning itself? The purpose of learning, and also give another even extra layer of uncertainty, right? When I was a graduate student, I started computer vision. I spent, the helicopter landing. Do you guys think which part is hardest? Control? No, it's actually not. Right now, differential equation is just another, a month work. Right? Calibrating the camera. Every single thing. We get into physical fights between students. Right? All the mechatronics symbol them. Right? Camera gets in. Right? Every time touched it, we get a physical fight. Right? Because which means I have to spend another half a day to recalibrate everything. Okay. So to get the hardware prepared, get the data prepared, then you know what you want to achieve, because that's the accuracy you have to get, right? Otherwise, you crash, right? Helicopter crash. Right? So those are the things I think, honestly, guys, this is, nowadays, if you want to have an impact, you have to know where the real problems are, right? Writing, that's why there are 10,000 papers submitted to NIPS, because their bar is too low, right? Everybody working on the same darn data, right? They're not making any innovation whatsoever. Right, even not thinking of the problem from a different angle, because you don't think about what you need. You think about what it can make the reviewer happy. Right, that's terrible.
How we train our students now.
Yeah.
First, you see how much time you actually spend in preparing your experiments.
Yes.
Versus writing. Yeah, you're actually the same story with I was a physicist, so my thesis was about studying the atomic, optical spectrum. Of certain radiation. That was basically a atomic physics experiment. But I actually spent 2 years building that laser.
Exactly.
Okay, purchasing wires, blowing tubes, and all those things. And we spent a lot of in literally 2 years building this whole laser system. And that experiment, that shot, took just a week.
Yeah.
Okay. And then analyzing that shot, even shorter, because we actually have all the equation compared. It's called proving hypothesis. We roll something or they force directly. We want that shot to prove my hypothesis. That's how physics starts.
That's also
that moment of experiment and the final result is very short.
Realizing things is hard.
Right here, I think
conceptualize things is easy. Right. Implement and really realizing things is hard. I mean, you can see that that's why, because we had this when we were graduate students, we're building those helicopters, right? And this now there's drones everywhere, right? DJI or even the 2 drones fighting over Ukraine, both from Berkeley, by the way. Even the Turkish company supplying the the drone for Ukraine, and also the Russians using DJIs, right? They're from the Berkeley, right? Because 30 years ago, there's a team of people decided to do it, right? You go through, cracks everything with very limited computation. You try to control the helicopter. We land on the battleships. I land on different things. Make that mature. Of course, it takes years to mature, make it easy and simple. But those are the things, if you want to make an impact 20 years from now, you just cannot download some public data sets. Think you can do something imaginary, magical with it, right? You have to, even industry these days dominated the landscape, right? Because they have their own data. They have their own systems, tools now, right? We academia has a hard time to compete now. And with the same game they're playing. But of course, then we have to define new games, right? I tell my students, right? They have now, right? The machine, we have now, right? So that's only we have to find something we are good at, right? To compete, right? What Google people will be missing, what the Microsoft people will be missing. That's your own opportunities, right? You cannot compete with, your weakness against someone's strengths, right? But hopefully here you have more resources. You can do more exciting, more ambitious things. But nevertheless, right? Try to be ambitious. Try to be different, right? Think about it in different angles. I think one thing I benefited a lot from this discussion with Yang Kong was that, if everybody's about fitting the labels, right? Can we just shift it? That's all we did. We changed the perspective a little bit, right? All the information, there's a whole theory developed to try to explain data fading, model fading, right? Information bottleneck is trying to explain what happens. Yes, it fits that. That theory explains data fading, label fading perfectly. But it's missing a piece about learning, right? What if you want to learn data that works for the classification, definitely not for generative, right? So those are the things you realize. It actually turns out things actually in research can actually become very, very simple, right? And to really look at the things that people, obviously the blind spot of everyone, right? Okay,
Thank you so much.
Yeah. Oh, Eric, this is for you. Yeah. So I give you some homework.
And everybody, I will have to read it.
Thank you, Eric.
Yeah, so that's a gift. Thank you for your gift as well. Yeah.
Thank you for an excellent presentation. Insights and the discussion. Also brought a lot of good things. Yeah. One of little question before I go. Yeah, and or two more questions. You spoke about non-stationary type of data, sets that are very, very high dimension. How about data that are moving in time, that are dynamic? Are you able to expand this to that particular?
See, I mentioned the end, right? So yes, some of our working on the obviously, right? So here is all, we just example, all static data, right? Images.
Yes.
Right. So there are structures. The one type of structure is thrown after. Of course, with sequence data, there's both structures. There's temporal structures,
yes,
right? Sequence, images also, right? 2D
speech,
location. That's what actually transformer is good for, right? But now if you think about it, the transformer is not doing anything different, right? It must be compressing something, right? No, but if you have a sequential data, you cannot just simply compress it, right? Because this is one sequence, I say the same sentence, 5 seconds later, it's the same kind of thing. But you cannot compress as it is, right? What you should do, you have to align them.
Mm-hmm. Yeah.
Hence, that's why transformer, there's a positioning code. Guess what they're doing? They must be compressing, align the data as well as compress it together, right? Go read the Wiener's book. The first thing that you do with any time environment system, you do alignment. That's why he's, all the Thomas classes is trying to do that. That's why he brain compress things in frequency. That's why position encoding is cosine sine. Why? Because even in the Redu network, you can read our paper on the Redu network. If you compress all the data with a shifty environment, treat all the shifty environments together, you compress them together, the gradient descent operator automatically becomes convolution, becomes shifty environment, becomes actually it's efficient to compute in the frequency. It's not for you to decide. It's the nature, the job. You try to compress, hence that's the best way to compress. Okay, good. Thank you very much. Sorry. Yeah, sure.